Good to see you again. I call myself Mr. U.S. Patil, working as assistant professor at Sharad Institute of Technology, College of Engineering, Edrao, Ichalkarji, Kolhapur district, Maharashtra. So we are here going to see transformations, 2D, 3D transformations. Before going to discuss transformations, we already discussed about the computer graphic softwares and previous videos. In that, we have gone through a general requirement of computer graphic softwares, ground rules, functions of graphic softwares, algorithm of line drawing. Everything we have discussed or gone through. We had discussed about a function of graphic software. In that, we have gone through some points. For example, or we can say that a generation of graphic primitives, and in that transformations also there, and weaving and windowing, segmenting, use of user input functions and all. So in that part, the transformation we are going to see here. So transformation means changing some graphics into something else by applying rules. Applying rules, we can have various type of transformation such as translation, scaling up or down, rotation, sharing, etc. When the transformation takes place on a 2D 3D plane, it called 2D 3D transformation respectively. The transformation play an important role in a computer graphics to reposition of the graphics on the screen and change their size or orientation. So here, if you see, if you get or we go through a homogeneous coordinates to perform a sequence of transformation such as translation followed by rotation, scaling, and we need to follow the sequential some processes. So here some processes are translate the coordinates, rotate the translated coordinates, and then scale the rotate coordinates to complete the composite transformation. To shorten this process, we have to use a 3 by 3 transformation matrix instead of 2 by 2 transformation matrix. To convert 2 by 2 matrix to 3 by 3 matrix, we have to add an extra dummy coordinator as a w. That is extra dummy coordinate we need to add in that. In this way, in this way, this is what 2 by 2 matrix to 3 by 3 matrix for 2 dimension. For 3 dimension, there would be a 4 into 4, and then one is a dummy coordinator as w over there, same as well as 2D. In this way, we can represent the point by 3 numbers instead of 2 numbers, which is called homogeneous coordinator system. In this system, we can represent all the transformation equation in matrix multiplication. Any Cartesian point, that P, that is x and y, you can say this bracket P of x and y. The x and y can be converted into homogeneous coordinator by P of x, y and h. This is dummy, we can say, or this is height of distance of axis, right? So here translation part, a translation moves an object to a different position on the screen, right? You can translate a point in a 2D by adding translation coordinators, that is tx and ty, that is tx in a x direction and ty in a y direction, to the original coordinate, that x y, to get a new coordinators to x dash y dash somewhere here. So it would be x and y coordinate. If it would be changed, that would be a x dash or y dash. From figure you can see here, or you can write that x dash, that is equal to this x direction, x plus tx, right? This is up to here is x plus this tx, this x dash equal to, similarly y dash is equal to this y, from here to here y plus ty, so that is y dash. The pair tx and ty is called the translation vector or shift vector. The above equation can also represented by using the column vector. We can say in a column vector p equal to x divided by y, p dash is x dash divided by y dash, and t is t x divided by t y. We can write it as p dash equal to p plus t. So we can write this p dash equal to p plus t, because x dash is again in terms of x plus tx and y dash in terms of y plus ty. So we can write this p dash equal to p plus t. So we'll see next the rotation part. Rotation part. In rotation, we rotate the object at a particular angle theta. You can say theta from its origin. From its origin. From the following figure, we can see that the point P, that point P xy, is located at angle of phi, right, from the horizontal x coordinate with the distance r from the original, with the distance r from the original. Let us suppose we want to rotate it an angle of theta. Yes, this is already there, and we want to rotate from an angle theta. After rotating it to a new location, we will get a new point, that is p dash of x dash y dash. Using standard trigonometric, the original coordinate of point pxy can be represented as, that is x equal to r of cos phi, and for y equal to r of sin phi. You already know that. So if y-axis we gone through sine, and for horizontal x-axis is gone through cos. So same way we can represent the point of p dash of x dash y dash for this. So we can write here x dash is r of cos this phi plus theta for this x dash, isn't it? This plus this, right? For y dash is same as it is, that r of sine phi plus theta. So we can write this x dash r of cos phi into cos theta minus r of sine phi into sine theta. So equation 3, similarly this is equation 4. From these four equations, from 1, 2, 3, 4, substituting of all these respectively means 1 and 2 in 3 and 4. 1 in 3, 2 and in 4 respectively. So we'll get x dash equal to x of cos theta minus y of sin theta. Similarly, y dash is equal to x sin theta plus y cos theta. So representing in the above this equation in a matrix form, that is x dash y dash, x and y coordinators, and this is cos theta minus of sin theta, and sin theta and plus cos theta, sin theta and this cos theta. Or you can say that this is, we can say p dash, and this is p, and this is r, we can say r. So r is a rotation matrix, r is a rotation matrix, that is cos matrix of cos theta, sin theta, and sin theta minus sin theta and cos theta. The rotation angle can be positive or negative. It might be. For positive rotation angle, we can use the above rotation matrix. However, for the negative angle rotation, the matrix will be changed as only the sign will be a change. This is what positive and this is what negative. If you want a negative, so just changing the angle, so that would be a negative. So cos minus theta is nothing but cos theta, isn't it? So we'll say a cos theta. Sin minus theta is nothing but minus sin theta only. So minus sin theta of minus sin theta is minus minus, that's plus sin theta, and cos of minus theta is cos theta. We know that. So this is what a rotation. Now this is scaling part. To change the size of an object, large or minimizing the figure, the scaling transformation is used. In the scaling process, we either expand or compress the dimensions of the object. Scaling can be achieved by multiplying the original coordinates of the object with the scaling factor to get the desired result. Let assume that the original coordinates are xy as usual. So xy scaling factors are sx and sy. This s is nothing but scaling factor, and the product and produced coordinates are x dash and y dash. This can be mathematically represented as x dash equal to x into sx and y dash is y into sy. We know this. So the scaling factor sx sy scales the object in x and y direction respectively. So sx in a x direction, sy in a y direction, that is means respectively. So the above equation can also be represented in the matrix form, that is x dash y dash, that is equal to x into xy, and the matrix of sx 0 and 0 sy, or we can say that this is p dash, or this is we can say p, and this is we can say s, because there is a scalar or scaling matrix. Now this is what a scaling process. The scaling process is shown here here. So we, if we provide the value less than 1 to the scaling factor s, here scaling factor s less than 1 value, then we can reduce the size of the object. We can say reduce the size of this object. If we provide value greater than 1, then we can increase the size of that object. You can see here. So next, reflection one is another point of reflection. We can say this this is object we can reflect over here in a horizontal axis from this side, and here in this side, and here is opposite side here, and this is symmetric, this reflection. The reflection is the mirror image. Are you getting this? This is what a mirror image of this. This is mirror. See here, 3 of 3 here, 1 is 1 here, and 2, and this 2 here. This is a reflection. See, this is 3 3 here, again is a 2 is 2 here, and 1 is 1 here. If suppose this is a mirror line, so object is here, so this is what objects in mirror, so that is what that is called mirror image. In other words, we can say that it is a rotation operation with 180-degree. In reflection transformation, the size of the object does not change, only reflection only happens, or mirror image, that's it. The following figure shows some reflection with respect to x and y axis. and about the original respectively. So this is some of our reflections. And next we can see that a rotation, as we see a scaling, rotation here, scaling, and another, this one is rotation of this two dimensional. And here now for three dimensional there would be a 4 into 4 matrices, as we see before. For two dimensions there would be a 3 into 3 matrix, and one is dummy one, and here is also one dummy matrix. So this 3D rotation is not same as 2D rotation, 2 dimensional rotation. In 3 dimensional rotation we have to specify an angle of rotation along with the axis of rotation. This is very important. And we can perform 3 dimensional rotation about x, y, and this is third axis, that is z axis. They are represented in the matrix from as form matrix form as below. This is rx, we can say rotational in x direction of that theta. This is ry in the y axis of theta rotation, and this is what z direction, that is rotation of theta. So this is what a matrix of 3 dimension. So this is the following figure explain the rotation about a various axis. This is what rotation about x axis, a rotation about a y axis here, and rotation about z axis. It might be like this or it might be like this. So we can see here this is proper image object, so we can rotating with a which axis, this is y axis, or we can say this would be a x axis of rotation. Next, the scaling, you can change the size of the object using scaling transformation, as we seen before for 2D. In the scaling process you either expand or compress the dimensions of the object. Scaling can be achieved by multiplying the original coordinates of the object with the scaling factor to get the desired results. The following figure shows that effect of 3D scaling, right? So this is what a 3D scaling. And for 3D scaling operation, three coordinates are used. coordinates are Three coordinates are used. Let us assume that the original coordinates are x, y, z, and the scaling factors are sx, sy, and sz respectively, and the produced coordinates are x, y, z as we know, and this can be mathematically presented as below, that is s. So this is sx 0 0 0 sy 0 0 and 0 0 sz 0 and 0 0 0 1. That we can say this is what p dash. We know that p dash equal to p into s. S is a scalar scaling factors. So p dash is nothing but x dash, y dash, z dash, and 1, that is equal to p means x, y, z, and this is 1, and s is scaling factor, this is what. So we can get this result, that x, sx, y, sy, z, sz, and 1. This is what the 3D scaling operation. So thank you. Will everyone will see us soon with the next topic. Thank you.